So first off, what we want to do is we want to look at what is the differential means, the definition of it, and how are we going to use it. So up to now, right, these expressions that we have talked about so far, dy over dx, which is the derivatives of a function respect to x, look at it as a single symbolic, right, part. And we don't in this sessions, we want to know what is this dy and then dx alone means. That's what we are interested in. Okay. So we need to know how to interpret dy over dx as a ratio of dy and dx, which is two separate values. Right? So that's what we are interested in on this definition. So as usual, right, we can say that let x be a fixed number. So I can say that here's my x, and for this function's f of x. So therefore, this has become my f of x value. So what happened is this dy, right, and dx, they are called the differentials. Okay. So the differential of x will become the independent variable, which can be assigned the arbitrary value, and the differential of y is become a dependent variable, which depends on the value of x and then dx. So what we are talking about is basically, if I'm having another point right here, right, and this will become the change in x become my dx. So this is x plus delta x. So dx and then delta x will be the same. And the change in y in this linearization functions, right, that will be considered as dy. So now what's happened is the slope of the tangent line, right, the slope of the tangent line can be interpreted as, dy over dx. So dy is a value and dx is a value. So when we talk about the differentials, right, if y is a function of x, where f is differentiable at x, meaning this function is differentiable at particular x, then the formula for the differentials of y is given by f prime of x times dx. Okay. And when the value of dx is not equal to 0, if we divide both sides by dx, then we will get back into the differential derivatives formats. Dy over dx is equal to f prime x. So now we can basically talk about dy over dx as a ratio, okay, and which interpreted as the rise over run of the slope of the tangent line. Is there any questions so far before we move on from here?
The recording has stopped.
Are we all okay with this? Okay, so now we sort of have a new formula right here, okay? The differential formula, dy over dy is equal to f prime times dx, okay? So we can basically look at as dy over dx as a ratio. So some of us ask questions like, this is two different values. Now we can look at it as two different values to interpret it, right? Right. And it is an operator. Okay. So continuing this, next thing is understanding, all right, the distinguishing between what is the delta y and what is the dy, the differential y. What are the differences? All right. So that's what we want to look at it.
This meeting is being recorded.
So another thing that we want to making clear is, the increment dy, which is the change in the y value of the functions. How is that different from the differentials? Right? So as before, let's say that this function is f of x, and so therefore right here, the a point x, I have a function value f of x, and since the function is differentiable at x, then we will be able to find out the slope of the tangent line at that point, and then therefore we can find out the equation of the tangent line at this point, which is, I'm using a, so I'm gonna go along with a, okay? So that way everything will be in the same thing. So at a, so we will be able to find out the slope of the tangent line at a. So therefore we will have an equation of the tangent line at a. So the equation of the tangent line is basically y equal to f of a plus f prime of a times with x minus a. Right? That's the equation of the tangent line right here. And now, what we want to find out is this, right? And this is the part that I mentioned, like earlier, how how the approximation is working. So now I want to find out the function value at a plus delta x on the tangent line. So let's call this point right here, right? And this is my a plus delta x. So if I found out the value at a plus delta x, that basically means I'm going to be substituting this a plus delta x into this functions, right? The tangent line equation. So that means y by input will be a plus delta x. That is equal to f of a plus f prime of a. And my x right here would change it into a plus delta x minus a. So when I simplify it, a and a cancels out, so it will left with delta x alone. Okay? So now the y value, right, the function value at a plus delta x on the tangent line is equal to f of a plus f prime of a times delta x. So from before, we know that, right, the change in x for this tangent line, we have differential of x, which is equal to the delta x. The change in y values on the tangent line, which is a to, this a plus delta a, that is talking about the differential of y. And this is basically can be looking at as, right, the change in y value, which is basically going to be looking at as y a plus delta x minus y of a. But we know that this y of a, right, the function value on the tangent line is the same thing as the function value on the curve of the function f. So this portion, that is also equal to what, f of a. So that's why we are seeing right here my y's, the change in the function value on tangent line from a to delta a, that is basically y of a plus delta x minus f of a, which is equal to what, my right hand side, f prime of a times with delta a. So let me stop right here, and then do we have any questions so far?
The recording has stopped.
Are we all okay with this so far? Okay. If you don't have questions, then I'm going to move on.
This meeting is being recorded.
So now what we want to look at is, how do we look at the approximation of the functions? So as you can see that this, the change in the function value on the tangent line from a to delta a is basically this part, right? And which is from here to there. Now, the change in the function value of f, now I'm talking about this part. Let me use the different color. From here all the way down to here, that is denoted as delta y. And this delta y is basically f of a plus delta x minus f of a, right? So you can see that there is a gap, right? There is a gap between this dy, right? Differential of y and delta y. Here's the gap that we are talking about here. And if you can minimize that, then our approximation will be better, right? So therefore, now what I can talk about is the change in the function value of the on the curve of f from a to a plus delta x. That is basically f of a plus delta x minus f of a, that which is what? Delta y. And now I can see that this delta y can be approximate with the differential of y, which is basically using this formula right here. The derivative of the f functions evaluating at a times with the delta x. So that's the connection, and then the distinguish between the difference between the differential of y and the delta y. What is the differences? Okay.